to record twice for some reason. I don't know why.
Oh, that's funny.
Okay, we're good. Yeah, and then, I can give you a copy and you can edit it or put it on your channel as well. So if you want to.
That'll be the plan.
Yeah. So nice to meet you.
Yeah, nice to meet you. I was in the middle of your Stern-Gerlach, episode that you.
Cool.
I haven't gotten quite to the punchline of that yet.
Yeah, I actually pulled up a bunch of stuff that we might talk about. I don't know, but that was one of the ones that I kind of pulled up. So we can talk about that if you want. I noticed you mentioned it in your book that you sent me. So, yeah. So that's interesting.
It's an instance of affected measurement, right?
Yeah.
Right.
Yeah.
So it's I haven't watched your whole video, but I get the impression that you're thinking along the same lines, basically.
Yeah,
right?
yeah. So, they made certain assumptions at the time based on, I don't know. Like, I don't know if I'm right or not, but I'm very suspicious of this, going up and going down. Like when you, we're kind of starting in the middle here, but that's okay. When you take, when I take a magnet and I pass it between two magnets, that magnet's going to align. It's going to align with these two magnets. And if it's just a little bit above, let me just, so there's this, what people are calling they're calling the inertial plane or whatever, some people, whatever, the center of the magnet, which I'm now referring to as a node. So there's another video you'll watch where you'll see I'm starting to call it a node, because there's a self-similarity between the what do you call these? The electron orbitals and the magnetic isopotentials. Okay, so there's a self-similarity between that. And so when you look at the Stern-Gerlach experiment in terms of what, basically what's going to happen at the wall here if there is, this isopotential there. Anyway, so we're starting in the middle a little bit, but because you brought up the Stern-Gerlach experiment, I thought I would mention that. So we can talk about that, or you can finish watching the video and we can have another discussion.
Let's discuss that once I'm done with the video, because basically this is one of those experiments where I have a lot of thoughts on it, but I think I'll just set those aside for right now till after I watch the video.
This whole like up electron and down electron language really bothers me. There's up electrons and down electrons, like really, and then if you turn it left right, then they go left and right. So it's now you have left electrons and right electrons. Like it's really
I mean, someone who really like puts a lot of theory work into this, they'd say it's not that simple. They'd say no, it's in a certain quantum state, and depending on the orientation of the magnet, then you're viewing that state from the perspective of different bases. And then the measurement will come out to that, either up or down with respect to that basis. That's their way of looking at it. But that it's the big problem there, and with many other things in modern physics, is that it's extremely mathematical, which is fine. But the problem is that it's only math.
They're using mathematical language. So as soon as they say the word basis, they're using mathematical language instead of physical reality, right? And so that's how so many things are like that.
And in my view, the key perspective, I think, is we don't want to be anti-math. There's a guy. Have you ever heard of Bill Gaede?
Bill Davies?
Gaede.
No.
With a G.
Oh. Bill Gaede. Gaede.
That's right. It's pronounced Gaede, I guess. So I've seen some of what he says, and he's basically he borders on anti-mathematics, which on some level you can't blame him, but on another level, like, no, that's wrong. We don't want to throw the baby out with the bathwater. So the key way of thinking about this Yeah, the key way to think about this is like the physics comes first. You identify a causal relationship first, then use the math only to describe that causal relationship.
Yeah. Yeah, you don't use the math to like prove anything, right? Math is just a language to describe. It should be describing, right? And then
I think math can assist with proof, like a mathematical nature can help with proof.
Yeah, it is parallel with the proof, but not the proof itself. I mean, I'm a computer scientist. I need math. I like my math. I need math. I don't always like math, but that doesn't mean I don't need it. I need it to do my job. I need the math, right?
Yeah.
But I don't like the language of math. There's some things about the language of math I don't like either, like the whole complex numbers. I've come up with my own way of, so I had to, I don't know, retrodate actually complex numbers. I had to do it from scratch in a way that I could understand because I wanted to understand it intuitively. And just looking at it algebraically, you don't get an intuitive sense of what it is. So if you go on my YouTube channel and you look up demystifying complex numbers, and then there's demystifying quaternions, it simplifies it that I could teach it to grade schoolers, right? As long as they can add and multiply, as long as they can do basic arithmetic, then they can do this, and so they can understand it. It makes more sense to me.
Interesting.
But, yeah, so you can check that out.
I will,
don't have time to go over that, but I think it's important to have a good foundation for math. And I think the foundation for that kind of math, complex numbers are injected into quantum mechanics and relativity. It's used everywhere. I think it's extremely important to have the proper foundation of what it is, or where it came from. Yeah. Where did they come from? What is the foundation of why, because the whole, and the language again, real and imaginary, using those words. Once you see my video and you see how I do it, you'll realize, oh, those are terrible terms because imaginary makes it sound like it's not real.
Yeah.
But imaginary numbers are just as real as real numbers when you do it my way. So
interesting.
The language gets really messed up.
Oh, wow. I'm going to find that right now. We should stop screen sharing so that the recording, shows us a little larger for everyone.
Oh, what do you mean?
Oh, if you stop screen sharing, then our images will be larger.
Yeah. Okay, so I just wanted to show you that. Yeah. Good idea.
And
so if you want to share a screen, we can do that.
Oh yeah, I'm sure I will. I'll send you a link right now. So this is very funny that you brought this up because last night I read the appendix of my mentor's book, and he says he talks about a bunch of issues in philosophy of mathematics, and he makes the claim also that complex numbers are fully real. And at first there's just, come on. And then I read it and I was like, holy moly, they are completely real. That's incredible. That's incredible.
Well, it's incredible that you were just reading that last night and I just mentioned it.
Yeah, so I have to show Ron. So I'll send you his book. So this book, it's not about math. It's not just about math. There's some math in it, but this book is called A Validate. What's that?
This is your mentor? Are you talking about your mentor? This is an important person to you?
Yeah, very much so. He's a philosopher, and this book is called A Validation of Knowledge. And what he means by that is it is exactly what it sounds like. It is the how we know. It is the answer to the question, how do we know? On the most fundamental level. Okay. So, you've read enough of my theory of induction to know that I'm giving like instructions for the scientist. Like this is the scientific method. My book presupposes his. I actually wrote this before I read his book, but basically one of the things I do is I kind of take it as granted that observation gives you knowledge of reality with certainty. And that's a fairly, controversial philosophical claim. There's a lot of people who have legitimate counter arguments to that. And Ron establishes why it is and the context in which your observations give you knowledge. So it's not just like, oh, you get to always just believe what you're seeing. It's that like he establishes the context that allows you to gain certainty in what you're seeing. And so that forms the foundation of my book, actually.
Yeah. Observation is an input, right? It's an input to maybe a theory, but you can't have a theory without observation.
Yeah. What he does is he validates observation, though. He shows you why and like how exactly a validation or an observation is valid, because there's plenty of philosophical objections. Like one example is like, how do you know you're not in the Matrix? Like that's kind of one of the.
And what if you're high?
What? Yeah, right. Right.
What if you're seeing something that isn't really there, which happens if you're doing a psychotropic drug or something.
So let's see. What's the name of that video with the quaternions?
Look up demystifying complex numbers. So look up the word demystifying in my channel, and then all the videos I do demystifying this, demystifying that. So
yeah, I got it. Here we go. Oh, cool. That's a quick one. Demystifying imaginary numbers. I'll do your imaginary one first.
Okay. Yeah.
And
a lot of these ideas, like I'm not going to say I came up with this myself. I rediscovered through a lot of hard work what complex numbers, what imaginary numbers really are. And so, imaginary numbers, real numbers are easy. You got the number line. We know what they are. They're real numbers. Imaginary numbers, I think just the language is the problem. Like we can use imaginary numbers and get good answers. And I use imaginary numbers for, to generate the Mandelbrot set. So that's where kind of the fractals, the fractal paradigm comes in. So fractals, I'm just going to put my screen up here. Right. That is my mentor. My mentor is the Mandelbrot set. And so my starting point, and I'll just get rid of that for now because that's not important, but that's my starting point. So my starting point for my cosmology, which is I'm calling fractal cosmology, is let the universe be fractal. If the universe is fractal. So my starting point is if the universe is a fractal of some sort, and maybe even almost exactly that fractal, then what would we observe? Kind of thing. So that's sort of my starting point. And so that's quite a bit different than what anyone else is doing. And then through, and then going back, and trying to figure out so the main property of fractals is the property of self-similarity. Okay. So, and then as I was reading your stuff, I was trying to think like, how would I word this, so that you can understand it. And so, basically what I'm looking for is what physics has the property of self-similarity. And okay, so that's my foundation. That's even for my foundation for the Æther, actually. And the answer is the magnet. Okay, the magnet has the property of self-similarity because when you take a magnet and I think I have a slide on that. Just a sec, I'll bring it up. It's easier to see here. So a magnet has a property of self-similarity because when you break a magnet in half, you get two self-similar magnets, similar, the same as each other, but self-similar to. So the word similar is very important, not self-same, but self-similar to the original magnet. And you break those in half and you get the property of self-similarity. You get a magnet that's self-similar to that one, that's self-similar to that, and similar to that. So the self-similar principle, the foundational principle, if the universe is a fractal, is the magnetism, right? So that's my starting point. And when I'm looking for, what is the Æther made of? It's made of magnets, dipoles, electron positron pairs. There's lots of ways of wording that, and so so that's sort of using a little bit of your inductive approach, because this is we know how a magnet behaves. We have experience with it, so this isn't something that I made up off the top of my head, right? That's how a magnet behaves. And so that affects how the ether behaves if the ether is made of, dipoles. And that's, a lot of people had that idea. So that wasn't even a lot of people had.
Doesn't Maxwell's model
Maxwell was,
effectively
little twirly things like he had this.
Okay, right. His were magnetic dipoles.
Yeah. Yeah.
Right.
And this,
Now,
and
have
I,
you
I am
read
thinking
Donald
of them. I
Chang's?
am thinking of them as magnetic dipoles, but at that scale, they would just be dipoles. They would exactly be, okay, I have a little demo here. Let's see if I can get this up. Okay, so this is a demo. This is like charge, showing charge. And the background is just the charge field.
That's really great.
Okay, but you see how the arrows would be the dipoles in my ether model, right? So the ether is filled with these like there's an arrow. Like I don't like the way they draw these, but this is a best example I could come up with off the top of my head of what my ether would be. And see how these are kind of pinned in place. My ether model, they're pinned in place. They're kind of pinned. So so it's a different ether model than the one that was disproven by the Michelson-Morley experiment. Michelson-Morley experiment thought of it like a gas that we're going through, and then there's going to be forces and that sort of thing, right? So this is a little bit different in that, we aren't going through the medium, we're just affecting the medium as we're going through it. And so it's a different, so
what do you mean well, we are going through the medium because we're
but not
affecting it as we go through it.
We're not pushing molecules aside as we're moving through it.
It's not made of ponderable matter.
Exactly.
I mean,
this is nothing like anything that we see. It has to be everything that matter is, ether isn't. So that's another concept that I'm working on. I call it the principle of incommensurability. And I got that term from Ken Wheeler. I don't know if you know who Ken Wheeler is. Have you heard of him?
Sounds really familiar.
Okay.
I think other people have been suggesting his work.
Ken Wheeler is, let's just say, an interesting character who actually, I would say, because of him, I started my YouTube channel. Because I liked what he was doing. I just didn't like the way he was wording it. I thought he had some good ideas, and he's very repetitive. He repeats things over and over again. He'll sit down every day and do his video, and he'll say the same thing over and over again that he always says every time. It's like there's nothing new. And so I wanted to push it further. I'm like, okay, I get it, but he's not doing anything sort of tangible that I can So I actually started doing a lot of my channel to try to explain what he's saying. So I have one video. So his book is called Understanding the Missing Secrets of Magnetism. And then I made a video called Understanding the Missing Secrets of Ken Wheeler or something like that.
Nice.
Understanding Ken Wheeler's Missing Secrets of Magnetism.
Okay.
So I'm explaining him, and he's trying to explain magnetism. So I kind of started with that. But he had this term incommensurability that he uses a lot, and I started studying that word, and then I came up with sort of my own principle of incommensurability, and that so it's kind of like black is not white and white is not black. Black and white are incommensurate principles, but everything that's important is in between black and white. So all the sort of emergent properties are between the two incommensurate principles. And then I mapped out all the incommensurate principles that I could think of in nature, like magnetism and dielectric. Magnetic and dielectric are incommensurate principles. Magnetic is not dielectric, dielectric is not magnetic, but together you can have a electronic circuit, that sort of thing. So it's a broad term, like a broad binning of terms. I took all the terms from physics and binned them this way, and it gave me a lot of insight into how the universe works. So it's quite a bit different than probably anything that you've ever seen before.
Yeah, that's pretty different from the way I think of it. The way I think of it is that it's strict, like all we know about the ether is that, well, we know quite a few things about it, but the most fundamental thing we know about it is that it's an entity. And we know that it's not the kind of entities that we've seen so far, where it's just it's made of matter. And the way we know, and I would say the way we know, well, I regard this as proven. We know it's not matter because we know that matter is at least in part a wave of this stuff. So it just violate, I don't know, if one thing is a wave of the other thing, it can't be made of it just doesn't make sense to think of it that way. So it is an entity because it acts and it can be acted upon. And so I have to turn this stuff off. I can't believe Apple hasn't gotten rid of this. So let's get back to your dielectric idea.
Okay.
I'm actually going to,
yeah. So, the ether would actually be a dielectric made up of magnetic moments, right? Everything that's in here, right? And so,
it's a dielectric made of magnetic moments.
Well, dipole moments. Let's call them dipole, just like a.
Wouldn't they be electric dipole moments?
They're polarizable. They're polarized
magnetically or electrically.
Well, because they're not matter anymore. Okay, so let me take a few steps back. I believe that these, whatever they are that make up the ether, can be thought of. You can think of, okay, so when electrons and positrons annihilate, okay, they don't really annihilate. What they do is they bind together and fall back into the ether. Okay, then they become part of this structure, whatever it is, this medium. And the only word we can use is medium. It's a medium. I know, like Chantal likes to think of it like an elastic solid.
But she acknowledges that the phrase elastic solid is only an analogy. She doesn't literally think it is that.
It's a good analogy. Like all mediums are good analogies, actually. Fluid is a good analogy. Like there's a lot of good analogies because of the waves that propagate in a medium. So waves propagate in a medium. If light is a wave, there must be a medium. And so then we just have to figure out what that medium is. Okay, and so I got this idea from studying the Bose-Einstein condensate, right? So I think I have a slide of that. And this is where I got the idea of like the entities being pinned in place. Because when you form a BEC, I'm just going to call it BEC because Bose-Einstein condensates, too many syllables, right? So the BEC, the way it forms is, okay, let's say we start from absolute zero. Then you have the BEC is like governed by a single wave function, right? It's got no little dots in it. But as they raise the temperature up, or they spin it, either way, it does the same thing. So let's say they're spinning it. So they have a 2D. These are usually just two-dimensional. They have these 2D BEC, and they begin to spin it. And as they spin it up, let me go to a different slide here. Because I've got little dots in there, and then you can see the dots better. So this will form a vortex. So what happens is you try to spin a BEC, but it resists change to angular momentum. It doesn't want to spin. It is trying really hard not to spin, but they're trying to spin it in their experiments. So these are experiments. So it's the other thing I got from your book is, you need to have experimental precedence before you can say something. So this is my experimental precedence. Okay. So when you spin a BEC, what happens is it does not want to spin. So it starts forming these little vortices. So what is it doing is it's dumping all of its angular momentum into these tiny vortices. And as you spin it up, then you get 2, then you get 3, then you get 4, then you get 5, then you get 6, and eventually you get a whole bunch of them.
And what are these dots? They're vortices?
They're vortices.
Okay. And what are these substances? Like, how many particles are they made of? Is it some macroscopic number of particles that are
macroscopically? Okay, so they would use something like rubidium or something. There would be a bunch. I don't actually know in terms of numbers. They would take a bunch of them and then they would cool like a gas, and then they would cool it down.
It's some large number. We're not looking at like the wave function of like 1 or 2 atoms here. This is like
so this is
quite a number of them.
A bulk of some material, like some gas that they cool down to absolute zero, and then they work together as one wave function at absolute zero. And then just above, if you raise the temperature and or spin it up, it happens in both circumstances, then you get these vortices. And the vortices are pinned in place. They're kind of pinned in place. So that's where I got the idea of, oh, maybe the Æther is pinned in place and not like a gas that can flow. So then the only thing that these objects can do is spin, just like in my demo here. The only thing they can do is spin. So in my Æther model, it's just an idea. It's just a concept idea, is if they're pinned in place, and the only thing they can do is, the only thing they have is angular momentum. That's all they have is angular momentum. And the only thing these dots have are angular momentum. So there's I like to make analogies, and that's, I bring things together through analogy. And so
these dots stay in place when the gas moves, is what you're saying?
Okay, so the other aspect of the BEC, and I've read a lot, and I may be confusing ideas because I've read so much that I kind of, I can't hold it all in my head all at once. But anyway, so what happens, so there is a phase transition. So phase transitions are really important in my cosmology. There's a phase, these are like little phase transitions. So the dots appear suddenly. So one dot appears suddenly, then they spin it up, and then boom, all of a sudden there's 2. So it's not like they gradually, they're the 1, 2, 3 phase transition. And then at a certain point, when they spin it up, there's another phase transition at around 2.7 degrees Kelvin, where so these vortices tend to be kind of paired. So you can almost think of them as vortex-antivortex pairs, and not just vortices, but that gets a little complicated. But anyways, the unpaired charges begin to form that can move around. So that would be analogous to electrons and protons in real life. So this gave me the idea that maybe the universe started at the diametrically opposite end of the thermodynamic spectrum at absolute zero, and for some reason it spun up or heated up or whatever, and then it went through these phase transitions, creating the background, which is the Æther. And then there was a phase transition at about 2.7 degrees Kelvin where the unpaired vortices, where the electrons and the protons and the unpaired charges were formed. So that's just, again, it's just a concept. I can't prove it. I'm just pulled a whole bunch of ideas together and thought, okay, maybe this is a possibility, right? So the 2.7 degrees, it happens with the BEC. It's approximately 2.7 degrees, where there is this actual phase transition that they talk about, where these vortices break up, and then it forms these charges that can move around and that sort of thing. And 2.7 degrees coincidentally happens to be the cosmic microwave background radiation temperature. So my idea would explain the ubiquitous CMB, because the whole universe would have to be 2.7 degrees before these unpaired before the electrons and protons could come into being. So this is before the Big Bang. So what happens here is before the Big Bang. And you might be interested, there's actually a book called Before the Big Bang by a man named Ernest Stern-Gerlach. So you might want to look that up, because I got this idea from him as well. So a lot of people, a lot of independent researchers fed into to these ideas. So his idea was very similar, where he had a sort of, before the Big Bang, the universe began as a relativistic electron-positron pair, he called it. And then it bifurcated, and then that bifurcated, and then that bifurcated. And then there was a phase transition in his model as well. So these little dots would be his electron-positron pairs, and that creates the background, which is the ether, the medium for the propagation of light. And then matter emerges from that. So yeah, so I got that idea from him. He's passed away now, but I did actually get to talk to him on the phone one time. So that was kind of before he passed away, because he actually met Einstein. Ernest Stern-Gerlach, as an undergrad, went to Einstein's house and had a conversation with him about his idea many years ago. Yeah.
Cool.
So he's an awesome. It's a good book. I thought it was pretty good, but got a lot of, I didn't agree with everything he said, but I don't agree with everything anyone says. I'm a puzzle piece collector, and I'm collecting puzzle pieces from, different researchers. And if something rings true to me, I'll put that in my, puzzle piece. And then eventually, like a pattern starts to form, kind of like the fractal, right? A fractal doesn't look like anything. You iterate once, and then you iterate again, and you iterate again, and eventually a beautiful picture forms. So I think that's how my mind works.
Okay, I see.
Yeah. So it's a lot. I can't explain everything like off the top of my head, but yeah.
Right. I this is the first time I've heard someone say, kind of bemoan something that I've noticed about myself, is like, I've now gotten to the point where, like, I've read so much that, like, I've forgotten a lot of it now. Like, I can't keep the whole context in my head at any one time.
Exactly. Well,
that's actually
Chantel Roth say exactly the same thing. Yeah.
That actually happened to me when I think the first time that happened is when I wrote my book, and then I looked at the table of contents, and something struck me. I was just like, how did I write this? Like, I looked at the table of contents. I was like, how did I write this? I don't know all of this. And then I'm like, wait, I do. It's just that I can't summon all of it all at once.
Yeah.
So
I feel the same way about my videos. I look back at my videos and I go, and I have to rewatch them. Like, well, I don't remember making that.
So I have a comment on this idea that the dipoles are stuck in place. Well, first of all, what does it mean they're stuck in place? Because motion is relative. Although maybe we don't agree on that, but like the only when I say place, I mean the same thing Aristotle.
Yeah. Well,
which is
these. I say pinned in place because they can be unpinned. I think I don't want to say stuck in place because it seems like they're stuck. I think they can be unpinned, and they can be like when, say, a particle comes into this field of view, then it would displace them, and then there would create some sort of a tension or some sort of, sensation in the medium, right? So they're pinned in place only when matter didn't exist yet. So before matter came into being, they would be separated, just like in the BC here. You can see, let's see if I can zoom in on this a little bit. You can see that they're, kind of equally spaced. They're in a hexagonal kind of a pattern. So when I model my ether, I put them in a hexagonal pattern because I think that was how they would naturally self-organize. They are under repulsion. And in the 2D, it makes sense because they're all spinning in the same direction. And that's why they're under repulsion. I'm having a hard time imagining how that would work in 3D, unless it's 4D. But in 3D, I have a hard time kind of how would they all be repelling each other in 3D. In 2D, it's easy. If they're all spinning, if these vortices are all spinning in the same way, they'd be like magnets pointing in the same orientation, and they repel. If you have two magnets side by side and they're in the same orientation, they repel. So it would be kind of analogous to that.
And I didn't realize that.
Yeah.
Oh yeah, obviously they repel. Okay, yeah, that makes sense.
Yeah.
Yeah. Well, I was gonna just float the suggestion that at least I'm not fully understanding this BCE, and I'm not and I don't have views on what happened at the start of the universe. I've heard really good philosophical arguments that there can't be a start, that the universe is eternal, but that, that it's eternal. I've heard good arguments for that, and this is one of the things I can't summon right now, it turns out. But so I don't have views, but I'm not convinced yet of that, and I just don't have views on all of that. But here's somewhere where I can make a suggestion, where considering your dipoles.
Okay.
You can think of your dipoles of your medium as stuck in place.
Mm-hmm.
I think you can. Here's why. Because maybe the whole concept of place means nothing more than what part of the medium is an entity in.
Right.
And so it's not that they're stuck in place, like there's a cosmic graph paper and like these elements of the ether are stuck in it. It's like, no, like the ether is space.
Right. Ether is space. 100%.
I shouldn't say it that way. I actually really don't like calling the ether space. I'll tell you why in a moment. But it's not that the ether is in space. It's that space is an aspect of the ether. It's like the ether causes spatial relationships.
Space is an emergent property of ether.
Yes.
I like to use the word emergent property a lot because it gets you a lot of it's when you say it is space, then you get into trouble, right? A lot of things are emergent properties. Like obviously these little dots are emergent property of spinning the BEC, right? And so, I think if there was a phase transition, so the Big Bang, the thing I like about the way I'm thinking about this is I don't need to deny the Big Bang. The Big Bang was just a phase transition. That phase transition that I was talking about, where matter comes into being, electrons and protons, is just a phase transition. And if you know anything about chaos theory, which of course I do because I'm chaos lady as well as fractal woman.
Is that your evil villain version in the mirror universe? Your chaos.
My evil twin is chaos lady.
Chaos lady.
Yeah. And so in chaos theory and in chaotic dynamic systems, there's always phase transitions, and these phase transitions happen suddenly and without warning. They're almost instant. You like when you do cymetics, right? Have you ever seen cymetics where they have a sound? They have put sand on a vibrating plate, right?
Yeah.
And they up the frequency and up the frequency, and then there's and then it shifts quickly to the next phase, and then it shifts quickly as you increase the frequency. And so I believe that I don't need to deny the Big Bang. I'm just going to call it a phase transition. And I actually heard someone recently, I think it was Neil Turok from the Perimeter Institute of Theoretical Physics. He's a cosmologist, and I heard him use the word phase transition, and I was like, oh, maybe he's catching on. So I think it was a phase transition. If there was a Big Bang, and obviously they're seeing something that looked like a bang. Phase transitions look like bangs. They look like bangs. They happen suddenly. They can be violent. They can, and they can also create fractal patterns. And so the fractal patterns can appear in phase transitions. And I have lots of examples of that. Some really good examples of that. Yeah. So that's where the fractals come from. And there's a chaotic phase from one phase to another phase. It breaks up into chaos, and there fractals appear. The property of self-similarity appears in that phase transition, and then maybe it transitions into another phase. But yeah.
Okay. I see.
So phase transitions play a big role in my idea of how the universe came into being.
And by a phase transition, you mean like a fundamental change in the way that the constituent entities relate to one another.
Yes, exactly.
And the fractal emerges from the fact that, like, maybe tell me if I'm getting this right, but I think I can infer a lot of this. I haven't studied fractals almost at all. Okay. So
most people haven't.
Yeah. So I would imagine that, like, let me think. Large groups of the entities interact with one another in a way that's similar to the way small groups of the entities interact with one another. And as a result, you get like one pattern at the macro level, which then gives rise to a smaller version of that pattern at a smaller level, which gives us rise to a smaller version of all the way down.
Yeah. So it's like the same laws of physics, but at different scales, which is nice because then you just have one law, but at many scales.
Yeah.
Right. And that's kind of how I see maybe the gravity and electrostatic charge, those laws. Right. One is for the large scale and one is for the small scale, but it's the same law. Right. The inverse square law. It's the same law. It's the same, like similar law. I don't want to say same. It's similar.
There's things about it that are certainly the same, but there are also things that are quite different.
They're self-similar. That's why I don't like to use the word same. They're self-similar.
Well, but electromagnetic interactions don't or like electromagnetic.
I'm just thinking of electric charge, like attraction and repulsion. Right? Attraction. Not magnetism, just charge.
So they both have the form of isotropic spreading. And so that's where you get the inverse square law, because it's like they're spherically spreading isotropically.
Yeah.
But like they're not like, they can't be the same phenomena though, because electromagnetic.
They're similar.
They're just similar, but they're not just similar. Like when I think of similar, I think of like, say, similar triangles where they're basically the same except for size.
Right.
Size is the only difference.
Sure.
But in this case, size is not the only difference. Like electromagnetic fields don't cause the inner durations of objects to
I'm just talking about electric fields.
I see. You're just talking about the isotropic spreading of the effect.
The spherical charge inverse square law. As soon as you say magnetic, then we have to deal with the magnet, and that's got different laws.
Yeah.
That's got different laws, yeah.
Mm-hmm.
Yeah.
But
so these, little dipoles in the ether, so would basically be the reason why, say, the iron filings line up around a magnet. The ether lines up, and then the iron filings line up with the ether.
Does this explain electricity or magnetism or both?
Well, that's more magnetism. So the magnetism would be, the magnet in this field would cause the, let me go back to my dipole figure here, right? So let's pretend this is a magnet. Okay, I can actually make a magnet. There we go. Now we have a magnet. Okay, now we have a magnet. All I did was take two charges and touch them together, and now I have a magnet. And then the field behaves very much like a magnet here. So it's got, right? So I can kind of, this is almost too coarse to show it. But the only
it is a bit coarse, but we can still see the general idea. Yeah. Especially for the audience, especially if you direct your eye away from the center. Then you'll from the center, then you'll start to see it.
Yeah.
You'll see
here's
that dipole.
So here's like two charges. And so you have the divergence of the field is not equal to 0 because you have divergence here and you have convergence here. So you have, maybe I'll put this further away. So you have divergence here and you have convergence here. So all the arrows are pointing in, all the arrows are pointing out. But then when I bring this close together, so now this arrow is starting to turn. And so now when I'm touching them, now I have the divergence of B is equal to 0. Because now the field goes through. Now we have like more like a magnetic field where all the the arrows go through.
Yeah.
So in my mind, when charges are coupled, then you get a tiny dipole in the ether. So the ether is actually made of like more like these guys.
Yeah. Do you view it as being made of electric dipoles or magnetic dipoles?
Well, they would be now. It would be more like a magnetic dipole, because and so then I get back to the electron-positron pair. So when an electron-positron pair annihilate, okay, I'm going to take one step back. I want to talk about something that's ponderable, an experiment that you and I can do that we know about, something we know about, and it's sodium chloride, salt. So in a salt crystal, right, when you take a sodium ion and a chloride ion and you build a crystal, sodium chloride crystal, right, when those two, when the sodium and the chloride bind, they lose energy, right? So the binding energy is energy that's lost. So if you have a sodium chloride crystal and you unbind, I think if you shine a 3.5 watt laser at it, it's going to start breaking the bond. So you have to supply the energy. You have to supply the energy to break the bond. Okay. But when they bind back together, when you take the laser away, they bind back together, then energy gets released into the medium of the sodium chloride. So that same energy that took to unbind them gets released when they bind back together. Okay, so the same with the electron-positron pair. When the electron-positron pair come together, they completely annihilate. They might as well, you can't see the medium anymore.
Interesting.
Right? But that doesn't mean
they're not that your there. Simulation does that.
Yeah. So this isn't mine. This is the PHET.
Oh, it's a FET. Oh, okay. I didn't realize
those guys.
Those Colorado FETs.
Yeah. I wish I wrote this because it's really cool, but it's still like, I'm glad I didn't have to, because I didn't have to waste time doing it. Someone else did. Yep. Okay. So anyways, so electron-positron pairs, in my mind, they annihilate and release the 2 gamma rays, right? Or however many gamma rays, probably 2 gamma rays. But they don't disappear. What they're doing, they bind together back into the ether, or they bind into the ether. They bind into the medium. They become part of the medium again. And in that process, they lose all their ponderable energy, which are the 2 gamma rays that we see when they do that. So, so this gives me an idea that maybe possibly, in analogy with something very easy that anyone can understand, sodium chloride crystal, they lose a little bit of mass. When they bind together, they get tiny little bit of their mass gets dumped out. And it propagates as a wave in the crystal medium. So it's a nice analogy, I think. And then and we know we can get electron-positron pairs out of the vacuum. They talk about it. They're called virtual electron-positron pairs. They know they exist. They have to exist, and they're everywhere. At any point in space, you can pull out an electron-positron pair, supposedly, according to the standard physics, right? So where do they come from? Well, maybe they come from the ether.
I think it's almost like, I bet we could take the existing pieces and prove that they come from the ether.
Yeah.
The hypothesis I entertain here is that basically we already know that matter is, at least in part, a wave of the ether. It may not be entirely a wave of the ether. It might be a wave pushing a particle around. Maybe that's a reasonable hypothesis.
Yeah.
But one way or another, part of what matter is a wave. And so it makes sense to me that you get these two different types of matter, positron and electron. These are just two different manners that the ether can wave, and when they come together, they produce a third manner of waving. That's my
and when waves superimpose, they don't annihilate each other either, right? When you have two waves that are going past each other, they do constructive, destructive interference, and they come out the other side perfectly good waves. They don't destroy it. They don't annihilate each other. The waves don't do it. So why would electron positron pairs annihilate? Like, they don't just disappear. They're still there. You just can't see them. It's easy to ignore something you can't see, right?
Well, couldn't it be that they are still there, but they're in the form of a light wave now?
Well, they're not moving, so. Well, it depends on what you think a light wave is.
So, like you're talking, we're talking. So, I mean, like,
this would still be. It might still be a vortex, right? So it might still be like a John Macken vortex, like a Chantal Roth vortex.
Okay.
Right? It could still be a vortex anti-vortex pair. So instead of just a vortex, so an electron is a vortex of some sort, like the simulations that Chantal does, right? So that doesn't preclude that from being true at all. It's just when the electron and positron come together, the two waves, because they're going in opposite directions or because they're out of phase or for whatever reason, they superimpose on each other. They bind back into the ether. It could still be, vortices of some sort, vortex anti-vortex pairs that, need to be, if you want to get them back out, you have to put the energy back in. So the energy would be lost. So it doesn't have the energy to manifest as an electron and a positron. You have to put the energy back in to make them, to spin them back up to the scale of the electron and the positron. So once these annihilate, they would probably be more like at the Planck scale. They'd probably be more like, what you see at the Planck scale, maybe. Yeah. So it's hard to mathematically, say what scale are these at, but there is a Planck scale, and there's a good chance that there's a Planck scale for a reason, and that might correspond to what scale these would be at, in the medium. Right. So small that we'd never be able to see it. We wouldn't be able to even invent a tool to see them. We can only intuit them.
You have to infer their existence.
Yeah, exactly.
Yeah. And that's one of the main things I'm really trying to do is, I entertain a lot of these hypotheses. I think about them. I treat them as puzzle pieces, as you said. And my goal now is to try and take these puzzle pieces and to see, can any of them be put together? We have quite a number of puzzle pieces that are known with certainty. And can we put enough of those pieces together to start proving some of the hypotheses? And I've made some progress so far with that. My most recent video, I proved the ether. I show that, based on what we know so far, we can infer that there absolutely is an ether. It's not just a hypothesis. We know it for sure.
Okay. So when did you release that?
That was the speech I gave at the PAMO conference.
Oh, okay.
And so I
was
released
that the one
it.
Was that, or was that the one you did after that? Okay. I watched her video. I watched her talk. It was fantastic. I love it.
It was really good.
So I'll make sure I watch your talk. It's on your channel, right?
Yeah, it's the last video. It's the last major video I posted.
Okay.
Yeah,
I'll watch that for sure.
It's a 40-minute lecture.
Yeah. So I believe there must be an ether. I think you and I got into an argument in the chat. I don't know if you remember that. Where I was saying,
right.
I was saying there can be an ether, and you're saying there is an ether, and then Chantal said there must be an ether, and I like hers better. There must be an ether. I agree there must be an ether. When I'm talking to physicists, though, I work in the field of medical physics, and I'm surrounded by physicists. So when I'm talking to these guys, I have to be really careful or I get in trouble. So for those people, I'll start talking about the ether, and I always know it goes the same way every time. Oh, the Michelson-Morley experiment disproved the ether. And I'm like, Okay, so I believe there can be an ether with the right model of an ether, and that way it's kind of, I'm not saying, there isn't or is, or whatever. I'm just saying, well, okay, there maybe there can, I'm just getting them to think, right? Maybe there can be an ether with the right model. Maybe, the Michelson-Morley people had the wrong model of the ether and they disproved it, which is a good thing. If it was the wrong model of the ether and they disproved it, that's a really good thing.
Yeah.
Right. So I kind of try to be less.
That makes sense when you're speaking with someone who hasn't like thought through everything you have yet. Then
just
it makes sense
believe.
to say like there can be
They
still, despite the
believe what
Michelson-Morley
they believe.
experiment. Yeah.
So that's just to be, I believe there must be an ether, and I think there is an ether. But if I have to be careful.
What does must be mean as opposed to there is?
Again, it's just one more level. Like, I don't think we can prove that there absolutely is. I think we can
watch my video and see if you agree with me that I proved it. Yeah. I mean, based on.
I don't want to make an absolute statement and then turn out to be wrong.
So, wait! I just realized I think you watched the video. So I proved the existence of the electromagnetic ether in an earlier video, like a few months ago, and it may have been the video where we were arguing in the comment, respectfully disagreeing in the comments.
Exactly.
Yeah, that's what I take. That's basically what I take to be the proof. I prove that there's also like the quantum aspect to the ether and a gravitational aspect to the ether. But in that video you saw earlier, that's where I prove there's some kind of ether, because I show there's an entity at each location and it changes in accordance with the nature of the entities at neighboring locations. That whole shebang. And I think you said something like, oh yeah, I remember your comment. You said, oh, this video should have been titled "How We Know There's an Ether." And I basically said, yeah, I probably should have done it that way. I was trying to like kind of pull in more layman with that video.
Yeah, exactly. You're trying to be like
more
general.
There's a reason I did it. There's a reason I leaned into that whole idea. Like, wait, I proved the ether. I should put that. And now on this newest video, I say it in big bold letters, proof of the ether. So
so that's you got to do that at some point. Say what you think it is, and
sure.
I like naming things. So.
Yeah, right. A lot of people are against labels, but that is, that is opposite the scientist, because you need to label things to identify their nature. If you don't label them, then you don't understand them.
With the ether, like, that word has been a little bit bastardized. So I like, it's a beautiful word, and it's a shame, right? Because it's a beautiful word. And so I just call it the medium for the propagation of light when I'm talking to people like that. Because if I say the word ether, they'll go, oh, Michelson-Morley, blah, blah, blah. So medium, there's a medium. I can't imagine. Okay, so the other thing I wanted to tell you about myself is I work in the field of 3D ultrasound. Right? So medical imaging, right? And so there's media. My body is a medium. Okay. So in order to
let's cancel the screen share again.
Okay, yeah, good. Thanks. So in order to create a phantom, so what we do is we build three-dimensional ultrasound imaging technology, right? So we actually been doing this for 30 years. So right at the very beginning of 3D ultrasound, we were working on this, and we came up with our own technique of doing 3D ultrasound. We got patents on it and everything. And so in order for ultrasound to work in the body, we need to know the speed of sound of tissue in the body, right? Which is, or if we want to do it in water, we need to know the speed of sound of water in water. And if we want to build a phantom that mimics human tissue, we have to make a phantom, usually out of like Jello. We actually make phantoms out of Jello. Agar, which is a Jello-like material. And we add stuff to it to get it to mimic the speed of sound of tissue, so that when we scan something When we scan a sphere, it looks like a sphere, that sort of thing. And we want it to mimic what. So I'm intimately familiar with the speed of propagation of a wave in a medium. Mm-hmm. And because I have this experience, I have like a strong sense of what that means. There must be a medium. If light is a wave, right, then there has to be a medium. There must be a medium. And I don't believe in photons, even though that is a big word in my field. Photons. Mm-hmm. We do MRI, they talk about photons. We do CT, they talk about photons. So
what do you think is causing those dots in the double slit experiment then?
The detector.
Mm-hmm. What aspect of the detector?
Just like what Chantal, exactly.
Okay, that's right. Okay, exactly, so you agree with Chantal on this. Yeah, that's
exactly what she said. And I was so happy when I heard her say that. Exactly what she said. It's the detector. And she gave the analogy of pushing the swing. And if you do it at the right resonance, it's going to push and push and push. And eventually the kid's going to fall off the swing. Right. Same with the detector. Right. If you're at a certain resonance, eventually it's going to poke something off the detector. It's going to make the electron jump up a level or whatever. Same with the photoelectric effect. Same thing. There's a certain resonance above a certain resonance or below a certain resonance frequency. It doesn't happen. Above a certain frequency, it does, or around a certain frequency, it does. Knocks those electrons off, and it's a resonant frequency. It's pushing at just the right rate where it pushes and pushes and pushes, and then it jumps off. So it's not a photon that hits it and it jumps off. It's a bunch of resonances at just the right frequency that the electron just, boom, jumps off. So I think exactly what Chantal said is exactly what's going on. So the quantization comes from the detector, not from the medium, not from the light, not from the photon.
Mm-hmm. Right? Do you think that electrons, protons, and neutrons are particles?
They are particles, if whatever you want to call it. It's a particle, but I do
by particle, what I mean is small body.
Solitons. I like the soliton model. I like John Macken's soliton model. I like what Chantal and I are. She's given me all her code, so I've been working with her code and doing the belt trick, and all that stuff. So I get that, and I've been following John Macken for quite a while. In fact, I just heard from him yesterday because I was wondering, and he's getting older, and I always wonder, is he okay? And then he emailed me. So I like his model a lot. He's very thorough. His math is good. So I like the soliton idea for particles. Yeah.
Mm-hmm. I do too.
And that's kind of like gets the Æther medium thingies could also be thought of as solitons, potentially.
You mean the medium is made of solitons?
Yeah, they could also be solitons. They could be
solitons in what?
In whatever the background of the BEC is. So remember the BEC?
So like the Æther is itself. So you think it's possible that the Æther itself is like made of a further medium?
Yeah, there has to be two. There has to be
two.
So let's get back.
I think it's conceivable, like it's possible that there's two.
Let's get back to the BEC.
Yeah.
Okay, so in the BEC, there's one BEC. Like when you cool it down, there's no dots. So that's like one BEC. I call that the background. And then when you spin it up, you get these dots, but the background is still there. Mm-hmm. The background is still there. So the background isn't nothing. The dots are, in my opinion, are the medium for the propagation of light. But they're also embedded in this background. There's a background. And that could be
and the Earth is apparently stationary with respect to this background?
No. Things are moving around. Once particles start forming, they can move around in space.
Right? Okay, so this lattice is moving. I would imagine that this lattice maybe looks kind of like a rolling golf ball, like the dots are kind of like moving across it over
Yeah,
time?
well,
Is
the
that
dots maybe get displaced, like in my other demo, not my demo, like in this demo, right? Where if I had a big thing in here, then maybe these arrows would spread out. They would get displaced by the Earth. The Earth, matter displaces ether in my model. Matter displaces ether. But matter is also made of a
wave in the medium?
A wave in the medium. So in the background. So this background will spin up an electron. So I don't think the electrons are made of the dots. I don't know. It's hard to explain. Right?
Okay.
But there has to be two. There can't just be one medium. There has to be two. There has to be a background, and then there's the foreground, which are the dots, and the dots are the medium for this would be the crystal solid that Chantal talks about, right? The dots. But there has to be
my reason for I actually have, this is not one of my leading hypotheses, but one hypothesis I do entertain is that there are, one of the hypotheses I entertain is that there are two media, and the first media is the media in which light and matter propagate, basically. Then that medium itself is a feature of a deeper medium. Now, why do I think this? Why, like, what's the evidence for why this might be the case? The reason is because the general relativity seems to indicate that general relativity says, like, space bends, right? Now they say space-time bends. I reject that. I don't think time is like interchangeable with space. I think that's just I think there's no evidence for that. Space is the position of an object with respect to another. Time is a relationship between events. Time is like and durations are processes of change. So it's just a metaphysical mistake to say space and time are interchangeable. So that's out. But I think, what's that?
I believe that too.
Yeah.
Yeah.
That's a very important, like, a lot of physics changes once you realize that what time is. Once you have an Aristotelian view of time.
I just say time is an emergent property of change. It's as simple as that. If change didn't happen, time couldn't exist.
Yes.
And so it's
I have a video with Dan Harris, who's working on some an alternate theory of special relativity, and we discussed this in one of my videos. That's great to hear we agree on that. But anyway, getting back to general relativity. So general relativity, I think it's reasonable to say that gravitation bends space, and then, gravitation bends space. I don't think it makes sense to say space is bending, but let's just say gravitation bends space, and then it changes the inner durations of events inside objects. It does both of those things in some way that's connected in such a way that you can model it with a weird ass 4-dimensional geometry. But that's just a model. That's just like a nice
math. That's just the math to make predictions.
Yeah. So space apparently bends, but one way to think of that is the following. There's a medium in which light and matter propagates. That medium can bend. Why does that medium bend? Well, the reason maybe that medium bends is because there's forces in the deeper medium that are displacing the parts that are constitutive of the electromagnetic / matter medium. That's one hypothesis I entertain. So there's two media. You're confident there's two media for completely different reasons.
And also, Yonel Denude, if you do a search, Yonel, Ionel, Yonel, he also believes there's two media, and his idea came from what's the name of the guy that discovered the periodic table? I can never say his name.
Mendeleev.
Mendeleev. I always say his name wrong, so I always want to make sure I'm saying it right. So Mendeleev predicted two elements before hydrogen.
Oh.
Right? Ether, and the other one he called electrogen. Okay, so I don't know which is which in, say, in my model, right? Where we're at the dot model where there's a
Someone
background.
sent me a paper about electrogen. Or no, you've mentioned electrogen in one of your videos.
Yeah,
I think.
I probably
Okay.
Yeah.
That's
so
where
yeah, so that came from Mendeleev. He predicted that, and then Yonel Dinu used it to come up with his ether model, which I helped him write software to animate, and I call that the ether circulation model. So at the time, and I still think this, that the only thing ether can do is circulate. So it can either just spin, right? When charge comes through, it can spin, or if in magnetism, in the creation of magnetism, ether can circulate, kind of like water. So Yonel's analogy was, how do water waves form? Water waves form, or water waves propagate, because the water molecules are circulating. Right? So the wind blows. So here's the analogy. So the wind blows, it causes the water molecule to circulate, and then they do it because the wind isn't blowing infinitely fast. It changes the phase, so it creates circulation at different phases, and then you get your wave. So if you watch the video, you see 100% what the analogy is. So in Yonel's model, the electrogen is the wind. The electrogen is the wind. Is the wind that creates that makes the ether molecules circulate, and that creates the wave.
I think you mentioned this briefly in your video on what might be causing magnetic fields to swirl around wires.
Yeah, that's the one. That's the one. Yeah, so that's close to where those ideas came from Yonel. So that was me simulating his paper, what he had in his paper. And I liked it. I thought, oh, this is cool. And when I write programs, I understand things a lot better. So I understood exactly what he was talking about. And I like that idea. I call it the ether circulation model. Ether can only circulate, but there's something, has to be something else that's blowing. And that might be the background stuff that I'm sort of imagining in this BEC analogy, right? But Mendeleev predicted two elements before hydrogen, which is interesting.
Yeah.
And Yonel has been able to actually simulate his stuff. Like what I'm doing are animations, not really simulations, and he's actually using finite element modeling to simulate his ideas. So he can kind of prove that he can create magnetic field, magnetic lines of force. He can create the magnetic field with this model. So it's kind of cool.
What was Mendeleev's? Do you know what was Mendeleev's evidence for predicting these two elements?
I don't remember.
Okay.
Yonel was the one that did all that research, so that would be a good question to ask him.
I see.
Yeah.
Okay. Huh. Yeah. Part of my theory is that a hypothesis really needs to have strong basis in prior evidence. It's not enough to just say, oh, this hypothesis, gets right results. And so I always want to hear what
was the experiment he did that made him predict. Yeah. Was there an experiment that he did to make him predict those two? And that I don't really know. It's something to look up, actually. That'd be really interesting maybe I'll ask Yonel if he knows. He did a lot of research. He's a physics teacher, so he's in the game. Yeah.
Cool. Well, I should go. I still have work to do tonight.
Oh dear.
But
where do you work?
Oh, I as a tutor, I
Oh
just
yeah,
need.
you're a
I have
tutor.
like
Yeah,
I have things I gotta
yeah,
do before
yeah.
I have other. I just like administrative things, mostly for my
Yep.
channel, actually.
Oh yeah. Okay.
Yeah, I'm. So, but anyway, it was really nice to get to know
Yeah.
you and to
Yeah.
hear your various hypotheses on this.
Hmm.
And
Thank you. Thank you for
uh,
letting me do this. As I don't have very many people I can talk to about this stuff. So we got Chantel once in a while and John Mackin once in a while. Some good people out there, but yeah, it's a lonely
yeah,
world for us thinkers.
yeah, and it doesn't have to be though. I think
Yeah.
what I'm something I'm really trying to do is to take. I met a lot of people I was really excited about at the PAMO conference, and something I'm going to be doing a lot of work on in the next 2 months, or I mean, however long it takes. But I'm hoping I can get it done in about 2 months. Is to begin organizing the efforts of people who are trying to identify the nature of the ether and see
Okay.
if, and Chantel has actually done some of that by accumulating all these puzzle pieces. And
Yeah.
what I want to do is to see if I can use my theory of induction, specifically chapter 4, I think is what might yield immediate results, to make new discoveries. And in my view, I already have done that by proving the ether, but I wonder if we can prove more things by
Hmm.
putting more of these pieces together
Yeah.
and integrating it.
That
So
would be great.
I,
I would love to be
yeah,
a part of that for
yeah.
sure.
So
Yeah.
keep it coming. I got to watch more of your videos
Okay.
to gather more of your puzzle
Hmm.
pieces, and I'll invite you to the Discord server that we make for that
Okay. Sure.
collaboration group. Yeah. So
Okay. Sounds
yeah,
great.
yeah.
Thanks.
Looking forward to it.
Okay. All right.
Yeah. Well,
Great.
great to meet you,
Yeah.
and
Yeah.
let me know
So
if you want to talk again. Yeah.
okay. So I will end the recording and then download it, and I'll send you a copy.
Sounds great.
All right.
Cool.
Talk
All right.
soon.
Until next time, Lori.
Bye.
Bye.